Let's see. No, that was the wrong side. All right, so today we're going to start looking at, well, we're going to start really diving into 3 dimensions rather than the 2D stuff that we've been doing until now. And we're going to start looking at kind of the point of view of our graphics program. That is, we're going to set up where we're at, where we're looking from, and how we can kind of set up our view in 3-dimensional space so that our eye or our camera is part of our calculations. We're going to look at how those calculations are set up and mainly just how we kind of work with those, not in code as such, but in our program, where these calculations happen, how we set them up, and kind of what numbers and objects we need to set up in order for this to work. Make sure. All right, so to just set up the OpenGL pipeline a little bit once more. We have the Vertex Shader. We have our clipping window to viewport mapping, which we've already looked at. And we have rasterization. So we're going to be looking at the Vertex Shader a little bit now again. The idea is that our vertices, our vertex list, we've used those a little bit now using the GL vertex function, where we say GL begin means basically we have set all the variables for our OpenGL pipeline. We don't need to do that between GL begin and GL end. We just do that at any time. GL begin means we've set it up. Now we're going to start sending vertices in. And GL end means, we're done with the running stuff through the pipeline. But instead of GL begin and GL end, we're going to start using vertex lists. So the idea is we have these vertices, so basically a list of XYZ coordinates. And we basically tell OpenGL when we want to run these lists through. OpenGL will take this list, take 3 points or a single point together and run it through the Vertex Shader, take the next point, run it through the Vertex Shader, so on and so forth, picking up 3 points together for triangles, 4 for quads, so on and so, 2 for lines, and running them through the rest of the pipeline. So what happens inside the Vertex Shader is that we have these different matrices that affect the vertices. Kind of the main geometrical transformations happen in these 3 main vertices. The model matrix, in these 3 main matrices. The model matrix, which we've looked at, that keeps track of the main geometrical transformations that we've already looked at. Translations, scale, rotate. That's the main transformations that we kind of load up, add on top of each other in the model matrix. So the model matrix holds all of those. When we're doing push and pop, we're usually taking the model matrix, storing a copy of that on a stack, continuing, getting that copy of the model matrix back in, so on and so forth. When vertices are run through here, the vertices that we send in here, which are in local coordinates, basically meaning that they are represented as if the model itself has its own center of the universe. Basically the model that some artist made, and he just made it so that its center is 0, 0, 0. Those are the local coordinates. Multiply them through the model matrix. And so at this point when we come in, we have local coordinates. At this point here, after multiplying through the model matrix, sent in here, we have what we call global coordinates. Or what I like to call global coordinates, at least. Meaning that our vertices, or the values for our vertices, are here represented basically in the global coordinate system. So they're represented in our local coordinate frame here. Our local coordinate frame is stored in this model matrix. Once multiplied through it, we've taken them into the global coordinate system. That means that even though we're not running vertices, a lot of them through this at the same time and kind of comparing them in this system, it's just one vertex at a time, we know that at this point, every single vertex that we'll go through in this model and in other models, they're represented in the same global coordinate system. So the model matrix has taken these things like where is this object and how is it rotated, and it's kind of eliminated that factor, taking it from its local coordinates to the global coordinate space. The next one is what we're going to be looking at now, which is we have the view matrix, which stores values related to the position and the orientation of our camera, of our eye. After which we have what's called eye coordinates. Eye coordinates are kind of doing backwards what the model matrix does. This is taken from local coordinates to global coordinates. We're going from global coordinates back to local coordinates, except not the local coordinates of the model, but the local coordinates of the camera. So the eye coordinates are the camera's or the eye's local coordinates. So we're basically taking everything and saying what we want at this point, before we continue, is to have everything uniformly represented in the camera's own coordinate frame. So the camera is the center of the universe, and the orientation of the camera is, once we're in eye coordinates, basically perpendicular and parallel to the axis of that coordinate frame. So does that make sense? I'm going to draw better pictures of this, but this here is what we want to do set up today. We want to say, how can you set up a way to go from global coordinates to the local coordinates of the camera? What happens finally here is what's called projection. And while we're not going to look at that until next lecture, the reason we want to have everything represented with the camera as a center of the universe and the camera kind of oriented perfectly parallel and perpendicular to its own coordinate frame is that the projection will suddenly become much simpler and much cheaper in calculating. Okay, so this is the idea. Let's switch over to the other side here and see if we can draw this up a little. So I have a global coordinate system here, where we have these actual axes. And we can imagine that we have some, let's draw it in 3 dimensions here. That we have some local coordinate frame here, where we have a point of origin. We have the vector A, the vector B, and the vector C. And we draw some object here. And what the model matrix does is that it takes the coordinates here represented in this coordinate frame, and it gives us the coordinates. So if there's a point here, we have some point like 1 something something in this coordinate frame. We get the coordinates for that in the global coordinate system. So we know where globally in our coordinate system this point is. Okay, another thing we have is we have a camera here looking at this. And it has some position and it has some orientation. And when we do projection, what we want to do is we want to say, okay, I'm drawing this kind of 3-dimensional sphere or what have you here, but I want somehow to take the part of this sphere, let's make this camera just a little bit bigger, whatever part of this sphere that will be seen on screen, and I want to project it onto this plane here, which is kind of like a screen in front of us, or if we imagine a window. we have a window in 3 dimensions. And what do I see through this window? Right at the top here, I see part of the window there. Right at the center, I see you guys. Below here, I see the camera, my laptop. Things will end up on places on this arbitrary window that I'm looking through. And that's what I want to map onto my screen, or I want to map onto my viewport in the end. So I want to project things to the point on this window that I see the things through. So if I see a particular vertex through this window, I can pinpoint exactly where in this window, what coordinates, what 2-dimensional coordinates are there on this window that I see that particular vertex through. So here's the eye. I'm projecting this vertex directly towards the eye. And this imagined window here basically collide with that or intersect that at some point. Okay, so that's what projection does. Doing this in 3 dimensions with an arbitrary camera oriented arbitrarily, rotated arbitrarily, is pretty costly. So what we want to be able to do instead is to say, what if, I'm going to say this is my y-axis here and this is my z-axis. What if I can set up a camera that is looking directly along the negative z-axis, and my y-axis is just directly up, and my x-axis is just directly to the right? In that case, suddenly projecting things towards the eye and finding out where they hit becomes so much simpler. Number one, we can do it independently in the y-axis and in the x-axis, because we don't have these arbitrary things and arbitrary vectors that we need to project in all dimensions. Instead, we can just say, all right, I'm going to project this in the y dimension in one calculation and the x dimension in another. It becomes cheaper, it becomes simpler to visualize, nicer to compute. Make sense? So we're not going to look at how we do this now. But the idea is to set up the camera, or not quite set up the camera. We make a transformation that will take this arbitrary camera and move it right down to here, or like right down to the center of our coordinate system. So we can imagine that this transformation would take this camera and stick it right like this. It'll orient it so that it's perpendicular and parallel to the axis, and it'll translate it so that it lands right in 0, 0, 0. Yes?
That's also orient the whole world, right?
That is exactly the point. So we'll make a transformation that would take this camera and orient it like that, but then we apply it to everything else. And what happens then? Then we basically get the coordinates for everything else in the camera's coordinate frame. So taking a transformation that would take the camera and stick it in the center of the universe, and instead applying it to everything else, means that we're basically taking everything else and setting it up in a way that we can allow ourselves to imagine that the camera is right at the center of the universe. Please, if there are questions, or if you want a clearer image of this. Here's the eraser. So let's just take these things out and say, all right, this is my camera, and I'm going to imagine this coordinate frame of the camera itself. So this is directly backwards, directly up, the other one would stick somewhere in here. And then I'm going to say, if I take this, simply orient it and stick it down here, so that instead of looking this direction, the camera will be looking from here directly into the whiteboard. All right? Take this camera here, and I stick it here, so that it's oriented so that it's looking into the whiteboard, oriented so that right is directly to the right, up in the camera is directly up, and backwards from the camera is sticking right out here. So the camera is right here in 0, 0, 0, looking in there. So imagine I can take the camera and stick it there. That means that I can take whatever object is in front of the camera, and if I apply that same transformation to those objects as to the camera, I'm representing them in the coordinate system as if the camera is in the center of the universe. And this is my objective. Basically take everything in the world along with the camera So I want it to be in the same relative place to the camera. Right now the camera is here and looking at something, looking at this pen. The image will not change if I apply the same transformation to both, right? The image that I end up with the screen is the same right now as it is here, as it is here. If I turn it around, I'm getting the same image because I'm applying the same transformation to the camera and to the object that I'm projecting onto the camera. Are we satisfied with the truth in this? So then I'm going to choose my transformation such that I'm going to make a transformation that sticks the camera right here in the center and just orient this along with it and say, I'm going to get the same thing on my camera if I project this onto this camera as if I project this arbitrary thing onto this arbitrary camera. So that's what I want to do. So I make a transformation that will take this coordinate frame and align it with the global coordinate system. And then I take that transformation and apply it to everything else. Sweet. Does this sound much like what the model matrix does? So what the model matrix does is it basically says, I'm making a transformation that takes some point that's represented in this coordinate frame. Here, this is the point, let's say 0.7, 0.7, 0.9, 0.2, something like that. This is a small point here. However, if I have a model matrix that represents this particular local coordinate frame, I am taking it out of these local coordinates and instead representing it in the global coordinate system, which is 1, 2, 3, 4, 5, 6, 7, let's say 8. Let me have black color then. 8. 1, 2, 3, 4, 5, 6, let's say, and down to here by like 1.5 or something. So 9, 6, 1.5, same vertex, same point, represented in different coordinate systems. I'm taking what's represented in local, I'm changing it to being represented in global. Fine? Now let's imagine that I have a camera here. Let's just add a color. So now I have a camera's coordinate system here. Something like this. Doesn't really matter. So I have a camera here looking in this direction, looking at this point. Now I've gone to global. Now I simply want to represent the same point in the camera's coordinate frame, right? Still the same point, but now we can imagine, okay, this is kind of going to the right. Let's say minus 0.1. And then, I don't know, whatever here, and then probably a pretty big z. It's fairly close to this, minus 0.1, 0.3, and then 1, 2, let's say 2.7 on z. Obviously, these numbers don't have to be exact, I'm just making them up. But you get the point. Same point, same position, different coordinate frames. But by representing it in the camera's coordinate frame, I'm really giving the camera ownership of the center of the universe, of the point 0, 0, 0. Once I've gone to red, then this point is 0, 0, 0. This vector here is I, which is 1, 0, 0. This vector here is j, which is 0, 1, 0. This vector here is 0, 0, 1, which is k. Okay, so represented in this coordinate frame, this is the center of the universe. Represented in global, this here might be, the position of it is something like 5, 1, 2, 3, 4, 5, yeah, 5, 4, minus something, 5, 4, minus 1. So this is the position of my camera in the global coordinate system. This is the position of the camera that I'll put in. And I'm going to call that particular name. I'm going to say this is my point I. The point I is the coordinates for the position of the camera in the global coordinate system. I need that. I need to know where it is in the global coordinate system in order to make the transformation that takes everything in the global coordinate system into here. The reason I have to kind of land in the global and not kind of go directly from local to I is just to make it clearer when we're kind of drawing it up and looking at it. In the end, if we don't have to do any calculations in between, which by the way we might, lighting calculations and such, but let's imagine just have to do this, it's okay to just take the model matrix and the view matrix and multiply them together. Say it's just one matrix, which is called the Modelview Matrix, which is kind of a native matrix in the regular OpenGL static pipeline. However, just in order to draw this, we're going to imagine we're going first from local to global, then from global to I, rather than just local to I directly. So, we represent the camera's position here, and then we represent its vectors here. So this here, while in this coordinate frame it's just vector 1, 0, 0, we're going to call it the vector u. This one, which is kind of the up direction, no, sorry, this one is backward. This one, v. So this is kind of our x coordinates. This would be our y coordinates, and then we have n, which is our z coordinates. So we have the vectors u, v, and n. Yes, question?
If you were to have multiple objects, would each object have its own local coordinate frame?
Yes, if I have multiple objects, then probably each object would have its own local coordinate frame. But they'd all end up kind of in the same camera's coordinate frame if they're being drawn into the same. So that's why we also like to decouple this and say, so this particular object is drawn here. So some model matrix takes it from this local to global and then to I. Even if we continue with the same camera, I might later draw another object, oriented differently, a different object in a different location. I'll give it a new model matrix. So that's why we're constantly changing the model matrix. We do translation, then scale, then rotate, then we draw something, then we pop, then we do another translation, scale, then we draw something, then we pop, then we do another rotation and a translation and a scale, and then we draw something. We're constantly, within the same frame, changing the model matrix. But while we're drawing kind of the same scene, we're usually using the same view matrix. That is the same camera. However, we can draw different viewports, different views, all kinds of things within the same frame. But in general, we're going to be changing the view matrix a lot less than we're going to be changing the model matrix. So it's nice to have the view matrix separate so that we can load identity into the model matrix, do all kinds of things to that. Then we just multiply them together again at the end and send it through. Or multiply our point independently through the model matrix and the view matrix. All right, this concept here, I'm just trying to get that through without making it too cluttered. But are we happy with the concept? I'm going to erase a lot of this stuff now and just draw a simpler image of our camera's coordinate frame. So I have a camera here, something like that. Obviously not very good at this. So it has a vector that points directly backwards from it, which is our n vector. Our n vector basically pointing like directly backwards from wherever the camera is looking. We have a vector that's pointing, it's difficult to do this here, n. We have a vector that's pointing directly to the right of the camera, which is u, which is like the x-coordinate. So me looking around, I have this u vector directly to the right, n vector directly from the back of my head, and from the top of my head. So this is n, this is u, I'll make it somewhere here. We have the y coordinate, the second coordinate, which is the v vector. So we have u, v, and n. And we have the point here, which we call I. So that's our camera. Our camera is represented as I, the vector u, the vector v, and the vector n. Just like the model matrix is representing a point of origin, the vector a, the vector b, and the vector c. It's just exactly the same thing. It's just a local coordinate frame. So what we need to do is twofold. Number one, we need a way to calculate these from simpler ideas. That is, if I expect a programmer to just set up the values for I, U, V, and N, it's no problem for I. But if I say, okay, it's pointing this direction, yeah, I can set up an N vector from like where it's looking. You know, then you have to calculate the U vector, calculate the V vector. You can't expect a programmer to kind of calculate this from scratch every single time. So what we want is kind of a way to calculate these from something that is intuitive for a programmer or a graphics expert to think about in terms of where the camera is and where it's looking. All right? And the second thing we want to do is to say once we have these calculated, we simply know where the center of this is, where the position of the camera is. We know its U, V, and N vectors. How can we set up the transformation, set up this calculation that will take everything and represent it in this coordinate frame? All right, so let's start with a little bit of a setup. As a programmer, what would you like to be able to say about the camera? Like, what are the simplest things that you can say about a camera that still kind of intuitively tell you where it's at and how it's oriented? You don't have to tell me the exact directions of vectors. Just if you were making a program, if you were setting up a camera here and just you're a director, you're going to tell the cameraman, what are you going to tell him?
Position.
Okay, so put the camera there. Fine. So that's basically I. Okay. We could do something like that. We could go and when you're setting up a first-person shooter, you probably end up with a camera where you want it to have a certain direction first, and then kind of degree by degree you're changing it. You're changing it incrementally. I'm going to go to what's more the type of thing that's done in animations. Like in a first-person shooter, everything is changed incrementally from the current state, which means I'm looking here. If I hit the right button, I just want the degrees to the right, to change, right? That's how I want the feel of the camera to be, because you have constant user input changing it. It's done a little bit differently if you're doing an animation. If you're going to say, yeah, like a director in a movie. Like, what am I going to say to the cameraman? Simple. Simpler than cardinal degrees and stuff like that. Just, I want the camera there.
What do you want it to like go? What do you want
Yeah,
it to
like,
see?
I want to look at that. Sorry, something else?
So the position of U vector and the rotation.
Position of U vector and a rotation, that would be like rotation, roll rotation. I think
rotation by the view vector.
Yeah. Those three things would probably suffice, yes, that would be enough. But it still feels unintuitive for me making as the director. So as the director, I'd simply say, I want the camera here, and I want it to look at that. Okay. We can do all the other things, but that seems pretty simple. So I, center, but there is one thing that you said that is lacking here. Because when I'm a director in an Earth-based movie, like the camera is probably going to be more or less oriented like this. I want it to be here, I want to look at that, that's enough. But out in space or in OpenGL computer graphics, you haven't told the camera how it's going to be like this. So how can we do that simply?
Using the rotation by the view vector.
Yeah, so rotation by the view vector, again, a little bit more complicated than what you need. Like, if I were the director again in this Earth-based film, where gravity is directly down, I can just tell you there's a vector that will always hold true. In this entire film, because I'm not going to do some surreal, weird rotation stuff, like the direction up is always this direction. So I'm going to add that as the third thing, up. So it's the vector up, because the rotation that you talk about and kind of an exact view vector, those aren't complicated to calculate. But still, if you're just an artist and just want to set up a scene in computer graphics, you just want to say, I want this to be here, I want to look at this, and I want my general up direction to be up. if I'm out in space, I start thinking about the other things, you know. Or maybe I just want to be walking on walls and then I set my up direction to this direction instead. But it's simple, because this up direction can hold true throughout my scene. I don't have to change that. I can change where I'm at, I can change what I'm looking at, but this up vector, I don't have to recalculate that every time.
You mean like if you have a camera facing directly backwards here?
Yeah.
If you look up,
Exactly. So if I'm just facing directly forward, if I have the same y coordinates on my eye and my center, where I'm at and what I'm looking at, then obviously this will be level, meaning that my v vector, which is directly up, will probably just be the same as a regular y coordinate, 0, 1, 0. However, as soon as I start looking up, it's like what happens here. If my general up direction is here, I just wanted to do it like this. I don't want it to, you know, do something else. So the up vector is basically just an anchor. If my up vector is here, I can look all over the place, and it's like an anchor up. It's like a reverse anchor, pulling me up so that my camera is like this. My camera doesn't go off camera like this. It's just telling me what's up. If I draw these things in here, kind of take the coordinate frame itself out again. So these are things that are just represented in the main coordinate system. I have my eye, I have my center, let's draw my eye here, and I have my vector up. So I is a point, center is a point, up is a vector. You can see though that if I say, okay, I'm looking here, this is not a right angle, this is not perpendicular. So the up vector is not the exact v vector. It's not going to be the same as what is pointing directly up from my head wherever I'm looking. It's just an anchor to that. But what does that mean? That it's like, okay, let's go back to the other vectors. Which one of these or the other parts of this coordinate frame? We'll take a 5-minute break now, but after that we're going to look at which ones of these do we have simple ways of calculating. Like from this original, from the eye, center, and up, like which one in particular is the first one that we can calculate? Which one's really easy to calculate? All right, let's take 5 minutes and meet back here. Já.
Er það bara beint upp frá myndavélinni eða er það bara alltaf beint upp?
Það er alltaf beint upp í heiminum, sem þýðir að það er ekki beint upp í myndavélinni. Sem þýðir að þú getur ekki sagt bara upp-vektorinn minn er vaff-vektorinn minn. Vaff-vektorinn er sá sem er alltaf beint upp með myndavélina, hvernig sem hún snýr. N-vektorinn er sá sem er alltaf beint aftur og bak frá myndavélinni. Og U-vektorinn er alltaf beint til hægri. En þú getur ekki bara sagt upp. Vaff er jafnt og upp. Þannig að upp-vektorinn er upp í heiminum en ekki upp á myndavélinni. En við þurfum að reikna þessa hluti út í ákveðinni röð, en ef við gerum það í þeirri röð, að þá erum við alltaf með upplýsingar sem þarf til að reikna næsta. Og það er ein grunnstærðfræði aðgerð sem við þurfum að skoða líka bara til þess að, sem það er örugglega skoðað áður en við skulum fara aftur í núna eftir hléið til þess að hafa það sem við þurfum til að reikna það. Hvernig tíminn eftir skráður búinn? 14:20 frekar en 14:30. 14:20, ok. Það eftir tæpan klukkutíma, 50 mínútur. Þá er líklega til hlýja það eins og snemma. Eða nei, náttúrulega þessar 5 mínútur sem á milli eru inn í tímanum. Þannig ef vel ætti að vera, ætti ég ekki að vera til 14:20 heldur til 14:15. Því að nýja stundatöflukerfið er þannig að það eru engar frímínútur á milli. Ég þarf eiginlega að muna eftir því.
Tímanum ekki að byrja á slæðinu?
Það hefur enginn sagt mér það. Og ég myndi að ræða þetta við kennarum daginn því að við sköruðumst þegar ég var að reyna að fara inn í stofu og hann út og við bara áttuðum okkur allt í einu á því, já, það er enginn búinn að segja okkur eigum að láta tímann að byrja 5 mínútur seinna eða enda 5 mínútur fyrr því að einhver staðar verður plássið að vera fyrir nemendur að komast á milli stofa. Ég er á upptöku þannig að ég ætla ekki að ræða þessar ákvarðanir þannig. En sumar ákvarðanir eru einfaldlega þannig að þær eru ekki beinlínis teknar. Þær eru látnar yfir ganga meira. Stundum taka tölvukerfi ákvarðanir fyrir fólk á þess að það átti sig á því að ákvarðanin hafi verið tekin fyrir það. Það er hægt að gera hluti ákveðin hátt en ekki hægt að gera það á annan og allt í einu er fólk fast í viðjum tölvukerfis og það er eitthvað sem að allir verðandi tölvunarfræðingar ættu að velta fyrir sér. Hvenær tölvukerfið er farið að hamla notendunum, bjóða upp á valmöguleikana sem fólk þurfti en með því kom einhvers konar limitations og hamlanir sem að fólk bara ekki þarf allt í einu að fara að lifa við.
Það er ekki eitthvað, ég held að það er eitthvað armur aðstofa fólk þegar ég það. Það er ekkert að framast þannig
Þú varst lengi að tyggja að það var
að tyggja þig, það var bara
nákvæmlega. Brjálæðislega flókin tækni sem hefur farið rosa mikil vinna í að fullkomna en geðveikt einfaldur hlutur sem hefur yfirsést. Sem að þessir menn sem gátu búið til þennan arm hefðu verið 5 mínútur að leysa.
Já, ég held að það hefði verið lagað bara strax.
Já, einmitt.
Það hýr alltaf einhvern veginn, það gleymist þetta eitthvað.
En það er eins, þú veist, kerfi sem getur raðað heilum skólanir og stofur og stundatöflur og kennara þannig að engir árekstrar verði er ógeðslega flókið kerfi. Fólk sem getur búið til það kerfi hlýtur að geta bætt inn möguleikanum á mislöngum hléum og þess áttar hlutum inn á milli. Því það er mjög auðvelt vandamál að leysa á meðan hitt er mjög erfitt vandamál að leysa. Hér erum við með kerfi sem að leysir geysilega erfitt vandamál mjög vel en leysir ekki mjög auðvelt vandamál og er þess vegna búið að setja í rauninni stundatöflu og tímasetningar skólans í fastar skorður sem eru ekki teknar, ekki valdar af starfsmönnum skólans, þetta er basically bara gerðust. Það er svona að einhverju marki. Þessar stundatöflur voru áður, það voru mislöng hlé, fyrstu frímínútur, aðra frímínútur með 10 mínútur og alls konar svona til að gera ráð fyrir mismunandi flakki á milli stofa á næsta tíma og þessu. Nú er bara fastur tími per kennslustund óbreytanlegt. Pínu, já. Herðu, ég var haldið áfram. Nú er þessi upptaka að koma með allt þetta rant hérna. Nú getur bara að vísa í þetta ef einhver spyr mig eftir. Ítta á fyrirlestur 5 í tölvugrafík haustið 2019. Þar er svarið við þessari spurningu. All right, let's switch to English again and put myself in the camera. So which ones of these would be very quick to calculate? Like, don't worry about the up thing. If you don't understand that, it doesn't even matter. The first one we can calculate just from where we are and where we're looking. Let's draw this again in here. So we have directly to the right u, directly up, but not the same as the up vector. We have v, And directly backwards from our head, we have n. Which one of these looks like it's simple to calculate from? So n is simply I minus center, right? If we do I minus center, we get a vector that is in the correct direction for n. We're going to have to normalize it later on. We're going to have to divide it by its own length so that we get a unit vector. But for now, we can say step 1, n equals, let's make these parts blue. Step 1, n equals I minus center. In some cases, I call this center point look. So look or center, I minus center, then we have n. So now the question is, now that we've calculated n, now I have to think about what the up vector looks like. And then we have to think about, like, what do we want now? Let's get a piece of paper or something. Here, fine. So let's imagine that I have my camera here, and I have this general up direction, but now I've calculated kind of the backwards direction. So this general up direction is here, this actual backwards direction is here. What am I doing now with these two directions? I'm kind of taking this plane book, this piece of paper, and I'm going to imagine that it expands in all directions, and I'm going to call it a plane in 3 dimensions. And I have n, which is directly backwards, and up, which is generally up. If they lie in the same plane, if I make a plane that they both lie in, can I make a vector from that gives me something? So let's look at planes a little bit. So we looked at lines in 2D, and we said we can represent a line with 2 points. We can represent a line with a point and a vector, and we can represent a line with a point and a perpendicular vector. With planes in 3D, I can say, how many points do I need to represent a plane? Like if I put 2 points here, in 3 dimensions, it's still a line. Right, I'm going to be in front of the camera here. If I have a point and another point, I just have a line, even in 3 dimensions. If I have a point and I want to lock down a plane, I can still rotate it around here. Points are solid, so I need one more, right? So 3 points, you can see this on the folder here. 3 points, then my plane is locked in. It can't be any other plane. So if this plane represents the side of a polygon or side of a cube or something, I can say if I have 3 points here, I can lock down this plane, and I know exactly in which plane this triangle that is between these points lies. All right, so 3 points. 3 points. I can say, like, how can I represent it here? Like a line is represented with a point and a vector. I need more. I need a point and a vector, still a line, and this might lie anywhere. But if I have a point and one vector and another vector, so if I have a point and 2 vectors, then I've locked this plane down, right? Fine. So a point and 2 vectors. Let's call these points here P1, P2, and P3. P2 is also P3 here. P1, P2, and P3. And let's say here I have the point P and the vector V1 and the vector V2. How can I change from this representation to this representation? P equals whichever, yeah, V1, fine. V1 equals, so a vector from P1, P2 is what mathematically? P2 minus P1. Okay, cool. And V2 equals, so I made this vector. Now I want to make this vector, which is P3 minus P1. All right, so I can make P equals P1, V1 equals the difference between the point that I chose and one of the other points. The second vector is the difference between the point that I chose and the third point. Now how about this representation, the point normal form? The point normal form, sorry, not the point normal dorm, point normal form in 2 dimensions said if n, which is some normal here, dot whatever point r minus b, which is the point that I choose here, if it equals 0, if this is true, then the point r is actually on this line. Now what happens with this representation, like if I have a single vector, if I have a point, oh, this is so bright here. I'm going to take the blinds all the way down. So I have a single point here, and I have a single vector that's perpendicular. Is that enough to lock down this plane? Can I now say any point that is actually in this plane, if I take a vector from the point that I chose to that point, and I take the dot product between these two vectors, that if it's 0, then the point is actually on this plane. I can be pretty sure. So the point normal form, rather than needing an extra point like the parametric form and the 3-point form, instead I can say, like, the regular 2 points will still be a line in 3D. A point and one vector will still be a line or a ray in 3D. The point normal form, however, once I add the third dimension, it changes from representing a line to representing a plane. So I can say like if I imagine, it's pretty hard to draw a plane somehow in 3D because it kind of extends in all directions here. But I have some chosen point, and something like this, where we kind of say this is perpendicular to this plane, like so. This vector n here is perpendicular to an entire plane. If I just take one vector and say this vector is perpendicular, no, it's not just perpendicular to a single line, it's perpendicular to an entire plane. I can also say it's perpendicular to V1 and it's perpendicular to V2 from the parametric form. The parametric form will then look like this. All right, P is not great here. We say A instead. I can say P equals A plus T1 times V1 plus T2 times V2. Okay, so we need 2 parameters. We have 2 vectors, all of that. We don't use the parametric form for a plane a lot. We use the parametric form for array a lot, especially in collisions and things like that. But it's more like a middle step to getting to the point normal form. So this is perpendicular to V1, and it's also perpendicular. Let's make V2 a little bit different here. V2, it's also perpendicular to V2. Like so. So now my question is, how do we change from this form to this form? How do we make V1 and V2 become this normal n? And now we're going to use something that I haven't defined yet in this class. But in linear algebra, have you is there a particular product between two vectors that yields a third vector that you've used? Cross product? Okay, so do you know basically facts about the cross product? So we're going to say here we have a cross product. The cross product, we can say is A written like this, A cross B. And I'll write down the formula in a moment. However, we can say the cross product, how can I write mathematically that the cross product and one of the vectors that the cross product is taken of are perpendicular? Like, how can I mathematically write one vector is perpendicular to another vector? Not quite. Well, like here, this is saying this vector and this vector is perpendicular, right? So if I just say the dot product, I can say the dot product of A cross B and A equals 0. And I can say the cross product of A cross B, the dot product of A cross B and B equals 0. Okay, so the cross product will be perpendicular to both the vectors that the cross product is taken of. I can also say the cross product of A and B equals the negative cross product of B and A. It's not symmetrical. That means that the cross product of V2 and V1 will actually give us this vector, this n vector as I drew it here. V1 cross V2 will simply give us a vector in exactly the opposite direction. So I'll write up the cross product itself here. I'll just do it in red to make sure that we see it properly. So A dot B 0. So A cross B equals, does anyone remember this? I don't expect you to.
AX times BY plus.
Okay, that is in one of the places, yes, but the first one is AY times BZ minus AZ times BY. I'm going to take this and I'm going to say that times the vector I, where the vector I equals 1, 0, 0, the vector J equals 0, 1, 0, vector K equals 0, 0, 1. So what I'm basically saying is the x-coordinate of AXB is this. Something multiplied with the vector I is obviously just that number as an x-coordinate. All right, I obviously will not manage to put this in all in one line, so just let's do it like this, plus. So instead of setting this up as this comma, the next one, comma, the next one, I'm just doing this times I plus this times something times j plus something times k. But it's basically x-coordinate, y-coordinate, z-coordinate. So for the x-coordinate, I used y and z. AY times BZ minus AZ times BY. So what's my y-coordinate going to be?
AZ times BX minus
AZ times BX minus
AX times
BZ. Yeah. Okay. The reason it's not X and Z, even though that would be the alphabetical order, is that, well, basically we're kind of moving one step to the right every time. We're taking, when we're calculating X, we're using the next one and then the next one after that. When we're calculating y, we're using the next one, which is z, then the next one after that, which is back to the beginning. And finally, this times j, and then we have ax times by minus ay times bx times k. All right, so this is how we calculate it, fine. But you don't have to remember this, just know how it works. Another thing here is that if we take these vectors v1 and v2, let's imagine that I put v2 here again, v1 here again. I make this patch basically. All right? So this patch here, the area of this patch, flatarmáli, the area of this patch has the same value as the length. So area of this patch equals the length of v1 cross v2. So we can imagine that if v1 and v long are fairly long vectors, the length of n will be somewhere in the degree of their multiplication. Basically, v1 times v2 will be something similar to the length. Not exactly. If they were perpendicular, it would be exactly. But no. So n is going to be really, really long for fairly long vectors. For vectors that are shorter than 1, n is going to be really, really small. So the length of n kind of goes all over the place with that. Now are the questions about the cross product in general. Now I want to switch back over to the other side here. Go back to where we were. And again, I want to say now that we have our n vector and we have this general purpose up vector. So n we have here, it equals I minus center. Okay, so what's going to be our step 2 here? What's the next one I can calculate? Do you feel I can calculate v, the one that's directly up? So I have one that's directly up from the camera. I've already calculated one that's directly backwards, and I have one that's kind of general purpose up. Like, what would the cross product of these two give me? Yeah, so they'd give me a vector that's, I have directly backwards, general purpose up. Perpendicular to those would be out of the right side of my head. So step 2 would be the u vector. So this is step 2, this is step 1. And what would the u vector be then? Does it matter if it's up cross n or n cross up? It does. What would happen if I used the wrong way around? Would everything go like way out of whack? Yeah, I'd probably just flip the sides of my screen. So right would be left and left would become right. So it's nice to do it in the correct order. We're using a left-hand coordinate system, so we can imagine that, well, I don't know what's the nicest way to think of this. What we can think of in terms of getting the directions right is this. I cross j equals k. J cross k equals I. And k cross I equals j. So basically, the x-axis cross the y-axis gives us the z-axis. And then we can just always move that one to the side. So we have the n vector, which is the z-axis, basically k, or these are the vectors we're looking at. Then we have something that kind of represents the directly up vector. It's not the correct one, but it represents it in this calculation. So even though these are not perpendicular, we can still get a vector here that is perpendicular to both of those. So they're not perpendicular to each other. We can get a vector that's perpendicular to both of those, and that will be our u vector. So that's going to be up cross n, like j cross k. Up cross n. So now we have two of these vectors. Obviously I is just going to be I. That's kind of the first thing we do. I in our coordinate frame is just going to be the I that we send in. What's going to be our third step now? Or fourth step if we look at I equals I as a step. So we've got this one. It is up cross n. How can we calculate v now? Now we have an actual backwards vector and an actual right vector. Yeah, so we can do, is it u cross n or is it n cross u? So u is kind of our I, n is kind of our k. So it's going to be n cross u. Again, if we do it the other way around, we're just going to kind of flip directions. Or up will be down, so everything's going to be upside down. Okay, so now we've calculated our coordinate frame. Does this part make sense at this point? Are there more questions about cross product, about why we use it, about how these points are found? So let's go back to here, since it didn't quite finish the idea of going between these formats. Going from this format over to this format, obviously we just have n equals v1 cross v2. There's an interesting question here though. How do we go back? Can we go back? It's easy enough to go back between here. Like v1 equals p2 minus p1 means just p2 equals p1 plus v1, and we can go back. In all of these we could go back and forth in 2 dimensions. Have we lost something here? Can we go back to the actual v1 and v2 that we calculated originally? We can't, because we have less data. We had a point and 2 vectors. We had 9 numbers to represent this here. Here we only have 6 numbers. We only have a point and 1 vector. It still represents the same plane, but we can't go back to the same parametric form. Can we go back to a parametric form? How so?
We just choose 2 points.
We can choose 2 points on the vector. We can actually take, we have n as a vector, like the point that we have here, b. That's simple enough. This is the point B. We just say B equals A. But we can take n and we can change it to V1 and V2. Like how can we don't even need to calculate particular points. How can I get a vector that's perpendicular to n? Like I need a cross product. Like if I take a cross product of the vector n and another vector, it'll be perpendicular to both of them, right? So how can I get a vector that's perpendicular to n? Take the cross product of n and whatever other vector. So I can just say, as long as n is not parallel to the x-axis, I can just take the vector 1, 0, 0. So I can just say I'm going to take the cross product of n and 1, 0, 0. Unless n is perpendicular to the x-axis, then I'll take the cross product of n and 0, 1, 0. Now I have one vector. How can I get another vector that's perpendicular to n?
Cross product between them.
Yeah, take the cross product between n and that vector that I got, the other perpendicular vector, and then I've got a vector that's perpendicular to both. So I can always go back to the parametric form, but I can't go back to the same 2 vectors. Either way. So we have this way of taking 2 vectors, doing the cross product, and we get a normal. And this is something that we're going to use when we need to calculate lights and things. That is, we have a polygon here, like a triangle. It has 3 points. It has 3 vertices. How can I calculate its normal so that I can calculate the correct light on it? Yes, I can take one of the points and decide that it's my main point here. I can take the difference between one of the other points and that point, and then the difference between the other two. Then I have two vectors. I take the cross product between those, and I have a normal. Now I can have a normal to any polygon that I have, and I can always calculate the correct lighting. But right now, we're using it for a different purpose. So I'd say at this point, we have U, V is here, V is n cross U. So that's our step 3. Step 3 is U equals n cross U. There's one more thing we need to do to all of these.
V.
V.
No, not that. No,
No, sorry. V equals n cross U. V equals n cross U. It's nice to know that you're paying attention. Thank you. There's one more thing that I need to make sure so that my view matrix makes sense. Some stuff isn't all over the place. And I need to make sure that these are unit vectors. These need to have the same length. They need to have unit length. So I need to normalize them. I can do that afterwards. Just say, n is my normalized vector. U is the normalized vector U. V is the normalized vector V. If I'm doing this in a program, I need to normalize 3 vectors. It doesn't matter that much because I'm setting up this view matrix probably at the beginning of my frame, and then I use the same view matrix throughout my calculations. So it's not like I'm doing this for every single vertex or for every single polygon. But still, can we optimize this a little bit? Can I somehow do fewer normalizations?
Our up vector was also normalized.
Okay.
We could just normalize n in the beginning.
Normalize n in the beginning.
And then up cross n is also a unit vector, and n cross u is also.
Okay, cool. This is the idea. It's not entirely true, though, that we can use it here. Because, like we said, if I have 2 unit vectors and I take their cross product, the cross product is not necessarily length 1. Because we can imagine that if they're not perpendicular to each other, say these 2 vectors, if each of this is 1, you can see the smaller this degree becomes, the smaller the area becomes. So this area is only 1 if we actually have a square with 1 length sides. But it's the correct idea anyway. We can't do it with up. If up is a unit vector, we can't trust that u will be unit length because up and n aren't perpendicular to each other. We'll have an n that's like this, u might be like this, then this area is smaller. However, it does hold true here in the last step. So if we just do n equals normalized n directly after this, then we do u equals normalized u directly after this, then we don't have to normalize v. Because n and u are perpendicular to each other. Because we used n in a cross product to calculate u, we know they're perpendicular to each other. V will then be perpendicular to both of them, so we'll have an entire system that is entirely perpendicular to all of this. Okay, so this auto-normalizes if we normalize these first. I would say calculate this, then calculate this, then normalize both of them, then calculate this. That's kind of the nicest way. For instance, if this one is really, no, it depends. It'd be nicest in a program to have these similar lengths. So if up is a unit vector and I and center are really far apart, you might want to normalize n right away to get these similar. Because the more difference that is between lengths of vectors like this, the more likely you are to get just kind of floating point offsets or errors or stuff in a program. In actual math, none of this matters. It will always be true. But in computers, we actually have a finite number of values that we can work with, and this can actually affect that. So normalizing each of these, then we don't have to normalize the last one. But at this point, we have this local coordinate frame here. And I'm just wondering where we'd like to just erase this. We kind of have all of this on the other side as well. So we had the data I, look, and center. No, sorry, I, center, center, and up. And we took that data and we changed it into our coordinate frame. So now we have our coordinate frame. Now the question is, how can I set up a transformation that will take this coordinate frame here and align it with the global coordinate system? Or, because we already know how to take our local coordinate frame and set up the model matrix, what are we doing differently here? We talked about go to this side here. We said that we're going from local to global with the model matrix. We want to go from global to I just being the local of the camera's coordinate frame. Now my question is, how can we make this nicely? To begin with, can we set up a matrix that does this? Can we just recap that? If I have point of origin equals my point of origin x, point of origin y, my point of origin z, I have the vector A, I have the vector B, and I have the vector C. Okay, so this is a local coordinate frame. Like this, I have point of origin, I have A, I have B, I have C. The matrix that takes coordinates represented in this coordinate frame and represents them, gives me the coordinates represented in global, goes from local to global. What does that matrix look like? Can you remember how exactly our coordinate frame itself is represented?
Ax, Bx, Cx, origin x, first row.
First, yeah, okay, AX, BX, CX, and origin X. Okay, this is the first row. So we just imagine, all right, I have my vector, I have my vector, I have my vector, and I have my point. AX, AY, AZ, 0 because it's a vector. BX, BY, BZ, sorry, 0 because it's a vector. CX, CY, CZ, 0 because it's a vector. Origin X, origin Y, origin Z, and 1 because it's a point. And here's my model matrix. This goes local to global, taking this and multiplying it with a point local X, local Y, local Z, and 1 gives me the point global X, global Y, global Z, and 1. All right. So this is my transformation. So what I'm asking you to do is to give me a matrix that gives me this transformation, going from something that's represented in here and lining it up with here. So basically, by multiplying this with 0, 0, 0, what is this going to give me?
Point of origin.
It's just going to give me the point of origin. By multiplying this with 1, 0, 0, 0, it's going to give me the vector A. Okay, same here. This is going to give me the vector B. This is going to give me the vector C. Are you getting my drift? If I take kind of the base vectors I I, j, and k, and send them through this matrix, I will get the origin vectors and origin point of this coordinate frame. So I'm basically taking my base coordinate system and I'm aligning that with my local coordinate system. By sending in 0, 0, 0 and 0, 1, 0 and 1, 0, 0 and all those things, I end up with my local coordinate frame. Here, I want to go the other way around, right? I want to take this coordinate frame, this camera, and we'll align it down to 0. So the effect I want now, if we set up a matrix here, say this is going to be the matrix M, some matrix here. I don't want it such that if I send in 0, 0, 0, 1, that I'm going to get I. I want to say if I send in I want to get the point 0, 0, 0, 1. Whereas here, if I send in the point 0, 0, 0, 1, I want to get the point of origin, which is the same as I in the local coordinate frame. Okay, so instead of going from global to, from local to global, that is 0, 0, 0 in this coordinate frame is here. In the global, it's the actual point of origin. So I want to go the other way around. So can I write this up?
And there's an inverse of the matrix yourself.
So I set up this matrix and I want its inverse, except now I don't want actually this matrix. What is the original, what is the same as this matrix for the camera going to look like?
It's going to be U, the vectors.
Okay.
And then the I is nothing.
So just before I write this up, I'm not writing up the correct view matrix, I'm writing up kind of the inverse view matrix now. That is, I'm writing it up as if it were a model matrix. U, Z, 0. Sorry, V, X, Vy, Vz, 0. Nx, Ny, Nz, 0. And I, X, I, Y, I, Z, and 1. So, matrix that I'm looking for is this one inverse. Meaning that I want a matrix that I can multiply with this matrix and it'll give me a 4x4 unit matrix. Identity matrix, sorry. Can anyone imagine what that'll look like? Just gonna make sure it'll show on the board. Yeah, I'll just make it really, really big. I'm not going to go through all the calculations of this, but it's actually interesting to take this matrix and the matrix that I'm going to write up now and actually multiply them together. You don't even need actual numbers. You can just use the I and A and B. And in the end, if you multiply them together, you're going to end up with 0 because of dot products and cross products, or dot products that will, that will become 0 because all of these vectors are perpendicular to each other. So their dot products will give 0. What it looks like is this: Ux, Uy, Uz, Vx, Vy, Vz. So this part of the matrix is just tumbled. Or transposed, I guess is the right word for that. This part of the matrix is just transposed. This part of the matrix is unchanged. This is still a linear transformation. So we're not going to get any skewing from this line. The only thing is what happens here. And I'll just tell you for now. There's no reason, no point in going through all these calculations when our heads have already been looking at these numbers for an hour and a half. So minus I, which is basically a vector that has the negative values of I. So we could also say what I call here minus I is actually the point 0, 0, 0 minus the point I, which will give us a vector. So this is a point. This is a point. But it will give us a vector with minus I x, minus I y, minus I z, and is a vector. Be strict on mathematics because the dot product is not represented for points but only for vectors. So minus I is this vector, minus I dot u. Here we have minus I dot n, minus I, sorry, dot b dot n. Okay, so this is the view matrix. If we simply have these vectors and this point, if we just have u, v, and n and I, then we make our view matrix simply by taking a matrix, we stick these values into the matrix in exactly this way, and we send it to our OpenGL Vertex Shader. And once there, it will be the view matrix. So after our vertices are multiplied with the model matrix, they will next be multiplied with the view matrix. In our kind of in the best lighting calculations that we're going to do, which will be actual kind of per fragment lighting calculations, we're going to do some preparation work between. So we will actually do the model matrix and then the view matrix and do stuff in between. So we can't just stick them together and use them as one. So we're going to do either lighting calculations if we do them per vertex, or if we do per fragment lighting calculations, we're going to do them in between here. Look at that later. So model matrix, then view matrix. If, however, let's say we're doing an animation, then usually this whole thing would be set up every time. That is, you're saying, okay, there's a thing that I'm looking at and there's a position that I'm at, and then I'm going to be moving these around. So every single time I'm saying, okay, I have a new position, I have a new center, I have either a new or the old up, and I'll calculate this and then put it in here. In a first-person shooter style game, where you have a point of view and you're incrementally changing it from where you are, then it'd be more common to actually calculate these in the beginning. Say, okay, in the beginning I'm going to be here and I'm going to look at that and I'm going to have this up vector. So we calculate this once. From then on, we don't calculate this again. Instead we say, I'm just going to incrementally change these vectors. I'm going to rotate the vectors within my camera in order for the camera's coordinate frame to change. So if I'm looking to the right, I simply incrementally change the coordinate frame. If I walk forward, I'm incrementally changing the I point. So I'm just working on these vectors in this point. Either way, every single frame, once I've actually either done the incremental changes to these, u, v, and n, or done this whole setup, however I end up with my current I, u, v, and n, I then simply stick them into the view matrix like this, and I have my view matrix and I throw it to the shader. And then it'll be there and do all the calculations that I need. Are there further questions on this? In the next lab class or in the next programming session, we are going to set up a lot of this. We need to basically set up everything that's happening in the Vertex Shader. And a very simple fragment shader as well, because if we're going to start using shaders, we need to set them entirely up. We'll have simple ways of doing the projection and doing the fragment shader, so we can kind of ignore that, just stick numbers in there. But we're going to have to set up the view matrix ourselves. So we're going to have to do these calculations. We're also going to look at how we can do these incremental changes. How can we rotate an entire coordinate frame? How can we rotate these vectors not around the world, but around themselves? Makes sense, because when I rotate in a first-person shooter, wherever I am, however I've already oriented myself, if I want to move to the right or turn to the right, I want this rotation to happen around myself, right? So we're going to look at how we do this. Or if I want to walk forward, I don't want it to happen along the x-axis or z-axis of the global coordinate system. I want it to happen along my n-axis. If I want to go forward, I'm going along my negative n-axis, right? So I'm oriented like this, and forward is here. Incremental changes. So we're going to do this stuff, and I'd really recommend trying as soon as you can to get this going. I myself am trying to get everything up and running in Python. I haven't done this shader stuff in 3D in Python before, so I'm just making sure that works. But I'm pretty sure that Monday I'll have that working. I'll have a description of how I made it work that you can then follow. If not, I'd still very much recommend that you show up in the class, because maybe a lot of the stuff that I'm doing will just be happening as we go. So I can't stick it all into some kind of step-by-step directions that I'll give you beforehand. So I'm hoping that by showing up for Monday's session, we can kind of get all of this going, get all the lumps ironed out, so to speak, to make sure that we all have a nice system and a nice flow to our 3D stuff. Because if we don't have some kind of 3D going on and moving cameras and things, then it'll be that much harder to get going on the next assignment, which will be soon after that. Any questions? No? Do you feel that this is clear, or? Fair enough. All right, I'll let you get out into your Friday.